Welcome to this explainer. Today, we're going to completely transform how you look at a simple glass of water. When you see a glass of water just sitting there on your kitchen counter, it looks like the most peaceful, static thing in the world, right? We naturally tend to trust what our eyes are telling us, that a calm liquid is just, well, a calm liquid. But actually, invisibly, right below that surface, it is an absolute battleground of chaotic, dynamic, thermodynamic forces.
So let's start with a bit of a provocative thought. What if I told you that by the end of this explainer, you'll basically have the conceptual blueprint to become a literal kitchen alchemist? Seriously. You'll be entirely capable of growing perfect, flawless geometric gems right at home just by understanding the hidden rules of how matter transforms. Specifically, we're going to zoom in on the magical, deeply mathematical world of crystal growth. And we're going to make those massive, invisible physical forces completely tangible for you.
All right, let's dive right into part one. The chaos below the surface.
To really grasp how a crystal is born, we first got to look at the extremes of how matter behaves, and how our standard, textbook definitions of solid, liquid, and gas can actually be completely subverted. When you start messing with energy levels, you quickly realize matter isn't neatly categorized at all. You get weird, rule-breaking stuff, like granular sand, which is obviously made of individual solid grains, but it pours out of a bucket exactly like a liquid. Or think about colloids like jello. It permanently traps water inside a wobbly solid matrix. Then you have non-Newtonian fluids like oobleck, which lock into a hard solid wall when you punch them, but flow right through your fingers when you leave them alone. And of course, there is plasma, where extreme heat literally rips electrons right away from their atoms.
A really brilliant way to picture how thermal energy dictates all this behavior is by thinking of it like a volume dial at a concert. At a low volume, you've got a solid. The atoms are packed super tightly together, basically just headbanging in place with a rigid structure. But crank that volume dial up, and the crowd loosens up into a fluid, sliding mosh pit. That's your liquid. And this specific shift in kinetic energy, that is the ultimate setup for all crystal growth.
That brings us to section 2, the tension of supersaturation. Now we need to look at the immense physical tension that gets created when we force a solid and a liquid to share the exact same space. The real magic kicks off when we take a solid, dissolve it into a liquid to form a solution, and then push it way, way past its natural physical limits. So how do you hide extra atoms in water? The secret is cranking the heat. Heating the water expands the space between the molecules, which allows you to cram in significantly more dissolved solid than would normally be possible. A regular cup of water can only hold a very specific amount of dissolved salt or sugar. It's just normal equilibrium. But when you crank that volume dial and heat it up, the liquid molecules vibrate faster, they spread out, and you can effectively hide a massive amount of solid atoms right in those newly created gaps.
Okay, so here is the crucial point. As that liquid cools back down to room temperature, the molecules slow down and they pack close together again. But now, they are trapped. They're holding an enormous, physically unsustainable excess of dissolved solid. The system is completely overloaded. This is a highly tense state called supersaturation, and it is desperately waiting for a release valve. As it cools, the system enters what chemists call the Lawmer model's metastable zone, building tension linearly until it hits an absolute breaking point.
And this kind of tension release happens everywhere in the real world. Think about the violent escape of carbon dioxide bubbles when you crack open a fresh soda. That's supersaturation breaking. Or when scuba divers dangerously get the bends from nitrogen gas nucleating in their blood. It even governs cloud condensation in our atmosphere, where the air gets so overwhelmingly overloaded with water vapor that the molecules are slammed onto microscopic droplets way faster than surface tension can throw them off.
Which leads us nicely into section 3, breaking the laws of physics.
So, if a liquid is holding way more dissolved material than it physically should, why doesn't it just immediately freeze into a solid block? What is holding back all that immense tension? Well, there are basically two ways a crystal can be born. The liquid is desperate to drop its excess cargo, but starting from absolute zero, which is called primary nucleation, requires a massive localized spike of energy. It's totally exhausting. Think of it like trying to start a massive viral trend on social media from a brand new account with 0 followers. It's really hard. But secondary nucleation? That acts like an effortless viral algorithm. If a microscopic shard or seed crystal is already in there, the algorithm just takes over. Joining an existing trend or structure is always infinitely easier than creating a brand new one from scratch.
But this actually creates a massive paradox with the second law of thermodynamics. That law dictates that the universe's chaos, or entropy, must always increase.
But crystallization takes a chaotic, messy liquid and forces it into a flawless, highly organized, low-entropy geometric structure. A crystal is basically a molecular prison. You are creating perfect order in a universe that mathematically demands chaos. So, how is this physically allowed to happen?
Here's the trick. To legally exist, the crystal brilliantly pays a thermodynamic toll. As the atoms lock into their highly organized molecular prison, they have to give up their kinetic energy, and that lost energy is released as actual physical heat, known as the heat of fusion, or enthalpy. So while the crystal becomes perfectly ordered on the inside, it literally radiates heat out into the surrounding water, making the outside environment far more chaotic to satisfy the laws of physics. It's an amazing trade-off.
And chemical engineers actually manipulate this exact enthalpy toll using these gargantuan machines. For instance, a basic MSMPR machine is essentially just a churning slurry tank that spits out a chaotic, random, mixed batch. But then you have the really elegant draft tube and baffle crystallizer, or DTB. This machine pushes the supersaturated solution up a central tube, letting the perfect, heavy, uniform crystals sink right to the bottom. Meanwhile, all the tiny, messy, unwanted primary microcrystals get swept upward, gently heated until they melt back into liquid and fed right back into the system to ensure perfect secondary nucleation.
Okay, let's move on to Section 4, Becoming a Kitchen Alchemist.
Because the cool part is, you really don't need a multi-billion-dollar industrial facility to control these forces. You can do it with common household items right on your counter. By mastering the exact same physical rules that chemical engineers use, you can dictate the architectural blueprint of matter in a simple glass jar. We use potassium alum, which is a super common, totally safe pickling spice. You dissolve it in near boiling water to create that super expanded mosh pit. But listen, the absolutely non-negotiable step here is filtering the hot liquid through a coffee filter. If you skip this and leave any speck of dust in there, the liquid, which is desperate for a gathering point, will use every single dust particle as a catalyst. It'll trigger primary nucleation everywhere and ruin your gem, leaving you with thousands of worthless cloudy specks instead of one beautiful crystal.
When the liquid first cools down to room temp, the supersaturation tension is at its absolute peak. Rapid cooling causes the atoms to slam together so incredibly fast that they form a chaotic polycrystalline mess with severe defects. But by extracting just one single clean seed crystal from that crude cluster, suspending it on a nylon string, and relying on painfully slow evaporation, we completely remove that initial thermodynamic tension. You're giving the alum molecules the necessary time to lock into perfect, defect-free alignment, eventually creating a flawless, single geometric lattice that looks like a precision-cut diamond.
Of course, nature fights back, so along the way, you have to fight some incredible environmental hurdles. For example, crystal flakes will literally defy gravity and climb up the glass walls through capillary action, so you have to manually scrape that crust away. Leaving an aqueous solution out for weeks invites biological slime mold, but you can brilliantly hack that by adding just one single drop of iodine. And finally, when your gem is done, you have to save it from dehydration. You literally paint your finished masterpiece with clear nail polish. This seals the critical structural water permanently inside the lattice so it doesn't crumble into white dust.
And if you really want to push the boundaries, you can actually hack the chemical architecture itself. Like you can use a dash of laundry borax to physically block the crystal's natural pyramid shape. The borax molecules absorb onto the points, acting as a roadblock, forcibly building a six-sided cube instead. Or try chromalum encapsulation. You can submerge a stunning but mildly toxic purple chromalum crystal into a totally clear alum bath. Because they share the exact same internal geometry, the clear alum will blindly build a perfectly safe, completely transparent glass-like shell right over the purple core. You can even grow clear crystals over a glow-in-the-dark pigment, so the geometric lattice basically acts like luminescent fiber optic cables. It's amazing.
Finally, let's look at Section 5, the crystallizer inside you.
For our final revelation today, let's step away from the mason jars and look at the bigger picture. We spent this whole time marveling at how supersaturation, temperature, and nucleation build these beautiful geometric artifacts. But the math isn't restricted to your kitchen counter. You are quite literally a walking, talking crystallizer. Your biology perfectly regulates the supersaturation of calcium and phosphate to construct your skeletal framework, your bones, and your teeth. But if the balance gets too tense, say your kidneys filter an excess of uric acid without enough water to dilute it, that liquid hits the unregulated Lemaire threshold. It nucleates, forms a seed, and slowly, painfully spawns a kidney stone directly inside you.
So, knowing all of this, knowing the hidden chaos, the strict thermodynamic barriers, and the immense tension of supersaturation, how do you view that calm glass of water sitting on your counter now? The next time you look at a simple liquid, don't just see a peaceful state. See the chaotic, immense tension just waiting for a microscopic catalyst. You are totally equipped now to look past the illusion of stillness. So keep your eyes open, observe the matter changing states all around you, and recognize the invisible, beautiful chemistry that literally builds our reality.